Welcome to another 2-Bit DaVinci video. This is part 2 of our series on the truth about Tesla's Model 3 batteries. First, we need to correct something from part 1. When we showed prices per pound, we accidentally divided the kilogram price by 2.2 instead of multiply. Here are the corrected prices. While our unit conversion mishap didn't lead to the loss of a $125 million NASA orbiter or anything, we do feel bad nonetheless. Rest assured, we'll do better going forward. Okay, so in part 1 we discussed the raw material supply chain and the battery cell manufacturing of Tesla's 2170 cells. Today we're going to pick up here and discuss how Tesla takes these cells and creates their world-class battery pack modules. First, you always want to start with batteries in parallel that form a brick. This brick on the long-range edition contains 46 batteries, while the base model will have 31 batteries. This is so that any single failure in a battery won't affect the core voltage of the brick. You'll just lose that amount of capacity and range. The next brick is inverted and joined to the first brick in series. All batteries that form a brick are attached in parallel via a bus bar. You'll notice that a thin filament is all that actually connects a battery to its bar. The reason is because of this thin gauge, it actually acts as a fuse. If too much current flows, either during charge or discharge, it'll overheat the fuse and break. This will remove the battery from the rest of the brick and isolate it from any further damage or potential thermal runaway event. For further protection, Tesla's 2170 batteries have 3 very small holes that act as vents to discharge the electrolyte to prevent pressure buildup and possible explosion. There is also a blue goo, which is added to further increase stability to the pack and prevent cascading failures. Speaking of thermals, we mentioned one of the benefits of small cells is the ability to better cool each battery. That's where Tesla's cooling manifold comes in. Tesla has a patent for a cooling manifold assembly for their battery packs. The cells are covered in a thermal interface material, which is a poor electrical conductor, but a good thermal conductor. That allows good contact between the aluminum battery casing and manifold. A water and glycol coolant mixture is pumped through this manifold, where heat from the batteries can be transferred just like liquid cooling for your PC or a conventional liquid-cooled gas engine. What's special about this design is the wavy grooves, which allow maximum contact between battery cells above and below the manifold, with minimal increases in flow drag. In the case of BMW's i3 prismatic batteries or Chevy Bolt's pouch batteries, this cell-by-cell cooling isn't easy to achieve. One limitation to this design is that the coolant will be colder when it first enters and warmer near the exit, leading to a slightly uneven cooling of a few degrees. This is why the wavy design that doesn't reduce flow rate substantially is so important. This means the warm coolant can be pumped to radiators more quickly. Keeping batteries cool as they charge and discharge is one of the most important factors in safe operation and also maximizes the usable life of lithium-ion batteries. You'll notice there is no radiator on the front of a Model 3, like in a petrol car, and that's because EVs don't need that level of cooling for the motor. However, look lower on the front bumper and you'll see vents that house the battery thermal management system and powertrain radiator. These motorized vents can open and close to minimize air drag, while also providing airflow for the radiators when needed. This can only drop temperatures to levels of the surrounding ambient air, but for especially spirited driving, super fast charging, or very hot days, the coolant can be ported through the air conditioning system through a plate heat exchanger for even better cooling. Tesla's Model 3 has a simplified 4 battery module system. Weirdly, they're not the same size, with the outer modules featuring 23 cell groups while the inner 2 modules feature 25. Again, this is the beauty of a small cell design that gives them this sort of flexibility. A recent teardown of a Model 3 battery pack by Jack Rickard reveals that each cell brick is 46 batteries in parallel, mated to either 23 or 25 other bricks in series. This means an extended range Tesla Model 3 has 4,416 batteries and weighs in at roughly 1,050 pounds. So the Model 3's entire battery pack has a capacity of roughly 80 kilowatt hours and a density of 167 watts per kilogram. Remember the 5-minute battery swap concept that Elon showed off a few years ago, where a Model S could pull in and have a robot swap battery packs in less time than a petrol car could fuel up? Well, it appears that idea is dead, because the design of the Model 3 batteries with their solid aluminum bottom plate won't allow for this functionality. But that's why Tesla has invested in DC fast chargers and their NCA chemistry combined with the brilliant cooling system and air conditioning exchange means Tesla Model 3s should charge quickly with few thermal bottlenecks. Along with their cooling system, the second factor is Tesla's world-class battery management system, or BMS. The BMS tracks the voltage on a cell level to ensure that the batteries charge and discharge evenly. It also monitors battery brick temperatures via strategically placed thermocouples, and is something Tesla now has over a decade of experience with. There are individual BMSs for each of the 4 battery modules. One of the great concerns with large lithium-ion battery packs is that a few individual cells don't discharge with the rest. Then the system reports low range and accepts a charge. But when this near full battery accepts a charge, its voltage will start to build up and cause degradation and could even explode. The BMS monitors this to ensure all the cells are fairly uniform and they have further protection with their individual battery fuses. Jack Rickard reported voltages within a few hundredths of a volt between all bricks in a Model 3 module. That's pretty impressive and a true testament to this crucial system in the Tesla Model 3 battery pack. On the back of the battery system, you'll notice a small hump. Tesla lovingly refers to this as the penthouse. To further optimize the manufacturing process of the Model 3, all battery-related systems for the entire car are housed in this compartment. In previous models like the S, the various AC/DC inverters and other electronics required for safe battery operation were spread around in various areas throughout the car. But now for the Model 3, this entire pack and penthouse is fully assembled at the Gigafactory and shipped to Fremont, where it can go into Model 3s more quickly with less assembly hours needed. This is a small innovation, but it really pays dividends when mass-producing Model 3s. So another question we always get is, my cell phone battery only lasts about 2 years before it starts going bad. Surely Teslas must have the same problems. The answer luckily is no, and the reason is two-part. One, most electronics like laptops and smartphones use LCO, or lithium cobalt oxide chemistry, because they provide very high energy density while suffering from a trade-off of a lower cycle lifetime. Most people only keep cell phones for a few years, and the manufacturers have decided that being small and energy dense is more important than being long-lasting. The second reason is that laptops and smartphones are charged to 100% and also allowed to discharge to 0%. This extreme state of charge and depth of discharge can really degrade the battery quickly. Again, in the case of your smartphone, it's more important that it lasts 12 hours and not 10 than it is to last 4 years instead of 2. Tesla Model 3s will help you charge and discharge at the best level for longevity. If you want to make your batteries last as long as possible, charge to about 80 to 90% capacity and only discharge to about 30%. If you're going on a long road trip, of course you can charge to 100% on occasion, but when your commute is less than your range, you should always try to charge to the recommended level. In the Model 3 interface, the one user-adjustable setting is the state of charge meter. A slider allows you to adjust how close to 100% you want the car to charge to. Remember that the voltage of a battery changes based on its charge. At fully charged, a 2170 cell has a voltage above 4 volts, while fully discharged only around 3. Also, if you remember from part 1 where we talked about the hybrid graphite anode, expansion and contraction from charge to discharge, it is again best to avoid the extremes. This user-adjustable charge level has led to some confusion and questions that we want to clarify. We've been asked if the base Model 3 and the extended range car actually have the same battery pack, and based on price, the added range is unlocked via software. This question arises because there were reports that Tesla unlocked extra range for people in Florida who were running away from Hurricane Irma. The story goes like this. Back a few years ago, Tesla was selling 75 kilowatt-hour battery packs at a lower price and locked the car's charge level to only 60 or 70 kilowatt hours. The idea was this made for a cheaper car and also presented Tesla an upsell opportunity. You have to remember they weren't making Model 3s yet, and they were getting creative about selling cars. So with unlocking the max range option, or in the case of Hurricane Irma, Tesla is able to flip a digital switch and set the car's state of charge meter to maximum. But don't worry, there's no such trickery in the Model 3. The Model 3 has 2 distinct battery packs, one with 50 and one with 75 kilowatt hours of usable capacity. There's no software magic at play here. So with amazing battery cooling, a state-of-the-art battery management system, and 10 years of experience, how long will your batteries last? Historic Tesla battery data suggests 95% range after 50,000 miles and 90% range after 150,000 miles. That means your 310-mile extended range Model 3 will travel 279 miles after 150,000 miles. That's after 11 years of driving at 13,500 miles a year. But the news gets even better because that historic data includes older battery packs. Our good friend Ben Sullins over at Teslanomics is a data scientist who has put together some real-world numbers from Teslas around the world. If you haven't seen his channel, we highly recommend you check him out. He's taken the source Google Sheet, which has been filled out by Tesla owners around the globe, and presented it in a great visual representation. Ben's website allows you to sort by kilometers or miles, or charge cycles, or vehicle age, and filter by different regions. You'll notice that all the data fits pretty well, and that almost all the vehicles seem to fit the 90% range left after 150,000 miles. There are a few outliers that have dropped to around 85% remaining charge after just 30,000 miles, and that's what we wanted to break down next. We've read a lot of articles about some Tesla owners needing battery pack replacements, and so we thought we'd break out the cars that needed new battery packs from this data. Filtering in this way reveals that about 6% of the cars needed a battery pack change, either for defects or possible excessive loss in range. What we found was interesting. Almost every Tesla that needed a replacement battery pack was manufactured in 2013 or older. Cars that were built more recently don't seem to have any of these issues, based on this telling, but limited data. Furthermore, every single one of the cars that needed new batteries had battery swaps within 8 years and 100,000 miles. Tesla is going to have a few bad battery packs. It's almost impossible to fully eliminate. All it takes is a few bad cells, a few bad solder joints, or bad sensors to cause potential issues. This has to be the single biggest downfall of Tesla's 2170 cell strategy. When you have to create an array of over 4,000 batteries, some errors are likely to arise. But here's the good news. If you do have a faulty battery pack, you'll likely catch that well within your warranty period. Tesla knows this and provides the warranty in accordance. Also, their process and mastery is only getting better, and Model 3 owners are likely to have the best results of any Tesla to date. Do keep in mind that petrol cars aren't perfect either, and we have the lemon law to allow owners to fully return cars that prove to be problematic. There are also thousands of reports of cars needing new transmissions or engines well below 100,000 miles. At the end of the day, it's an engineered and manufactured product, and as humans, we've never made anything perfectly and never will. What's more important is that rates of failure are low and that companies rise to the occasion with great warranties. Tesla is doing well on both accounts. The next biggest question we get is about cold weather performance. So why is cold weather such a concern for EVs? Well, the reaction happening inside those lithium-ion batteries is a chemical one, and one that is dependent upon environmental factors like temperature. So the battery thermal management system is crucial here as well. One thing to note is that for the Model 3, Tesla has ditched the dedicated battery heater. Instead, they have opted to warm the coolant via waste heat created by electronics and powertrain systems. That includes the electric motor and the AC-DC inverter. So the battery system and the powertrain both share the same coolant loop. This architecture makes Model 3 coolant systems more simplified and efficient than previous models. Unlike cooling a battery, where coolant is passed through either the air conditioner stack heat exchanger or front radiator, when heat is needed, the coolant is pumped through the powertrain cooling system. You might be wondering what happens when the car is parked and not running. It turns out it's the same process, only now electricity is intentionally wasted in the powertrain and inverter in the interest of creating heat. This heat is gathered by the coolant and pumped through the batteries. Your Model 3 can be programmed to keep the batteries warm in this way until the charge level drops to about 20%. But heating the batteries in the cold isn't the only EV downside. There's also the passenger cabin to contend with, and this is where petrol cars have an odd advantage. Internal combustion cars are so inefficient that about 80% of the gas you burn is actually wasted as heat. This waste heat makes heating the cabin incredibly easy, and is a weird advantage that EVs just don't have. Tesla electric AC motors are between 80 and 90% efficient. So, what is Tesla to do? They could have just put in a simple, inefficient, resistive heating element like the ones found in Chevy Volts and Nissan Leafs. But they actually thought about this and have filed a special patent. Their patent describes a system where the waste heat from every system that needs liquid cooling, including electronics and powertrain, is used to heat the cabin instead of just discarded. And they have a conventional resistive heater too, but is required to run less due to the heat pump system. Using electricity to create heat is a very expensive operation, and in most EVs in sub-freezing temperatures, range can be reduced by about 50% due to heating requirements. With Tesla's clever waste heat pump, your range reduction will probably be closer to 30%. So your 310-mile extended range Model 3 will deliver roughly 200 miles of range. This figure is hugely temperature dependent, so find out how cold it is where you live and ask the specialists at Tesla to get the best information possible. Let's put this into a little bit of context. In freezing temperatures, a lot of petrol cars won't even start, while you and your Model 3 will be just fine, albeit with reduced performance and range numbers. Also, you've probably seen outlets outside restaurants and grocery stores in places with freezing winters for petrol cars to plug in and run an engine heating pad. This pad keeps the engine warm enough to turn over when started. In the future, when we have millions of EVs on the road, we might very well have a similar situation where EVs will plug in to keep the batteries warm and charged while you visit your destination. And in many places, these electrical facilities are already in place. A couple of things you can do to extend your cold weather range is turn the heater down into the 60s, not run the seat heaters, and make sure to charge up as often as possible. Just remember you have a finite amount of energy, and it's up to you to balance range with comfort. Oh, and if the batteries are cold, that will also reduce the rate of regenerative braking. This is again because in cold weather there's more resistance inside the lithium-ion battery, and they can't react as quickly to convert the electrical energy into chemical potential in the battery. So when you first set off, regenerative braking will be greatly compromised, but as the system warms up, more performance and regenerative braking will slowly return. Here's some data from the Canadian Tesla owners, showing how much they've driven and how much of their original range is left. You'll see there isn't much of an effect, and the amount of charge remaining after hundreds of thousands of miles is pretty amazing, near 90%. Our advice: if you live in a very cold climate, you'll probably want to get the all-wheel drive for the added traction and also the long-range battery for better cold weather range. So with Tesla's BMS and heating magic, you can rest assured knowing your batteries will operate effectively for years to come. If you live in a very hot climate, the information is much simpler. The BMS will keep the batteries at comfortable limits using the AC loop if needed. Also, unlike the 30% drop in range in the cold, running the AC to cool the cabin and batteries should only reduce range about 5 to 10%. So let's wrap this up by reiterating a few points. 1. Tesla is about to mass produce EVs and lithium-ion battery packs at scales never before seen. In response to their success, other established automakers will increasingly build EVs as well, and this is going to put incredible strain on the battery raw material supply chain. A study done by UC Berkeley in 2011 states that just with lithium reserves already on hand, we could produce 1 billion 40 kilowatt-hour battery packs. If Tesla packs are twice that size, that's still 500 million cars with just the reserves. Other materials like cobalt and nickel are going to get increasingly critical, and the future is less certain. Everything has a cost, and while Teslas don't pollute directly, stay tuned for a future video on just how clean EV emissions truly are. They do have other environmental costs. We'll need continuous lithium-ion battery enhancements, but we'll also need crazy game-changing energy storage advances that will finally, once and for all, sound the death knell for the petrol car. There are future technologies like solid-state batteries that will become mainstream, and who knows, maybe something we haven't even yet dreamed up. But it's a bit of a chicken or egg situation where battery research is small because EV sales are small. EV sales can't increase until battery research and development increases. So Tesla decided it was done waiting around and took matters into their own hands. Tesla has already started to steal sales from premium cars like the BMW 3 Series, and will only continue to do so in the future. They have moved this gargantuan industry forward against such heavy inertia, and we can safely say the future is proving to be most exciting indeed. Thank you so much for those of you who've made it all the way through both parts of this video. Thank you to all of our new subscribers, And we wanted to also let you know about our Patreon page. We've spent over 100 hours researching for this 2-part series, 100 hours of 3D modeling and rendering, and another 30 hours in video editing. This is incredibly time-consuming, and we're doing it at the cost of sleep after our day jobs. It's simple, really. We want to make more content for you, but we need your help. If you kind of like us, we hope you'll hit the thumbs up and subscribe. But for some crazy reason, if you really love us, check us out on Patreon and consider becoming a patron. If we've helped you with your Tesla decision, we hope you'll consider using our Tesla referral link. If you don't want a Tesla or have other questions about any of this stuff, that's fine too. Whatever questions you have, you're probably not alone. We're 2-Bit Da Vinci. Thank you for watching.